Hello everyone, I'm Eitan Kosman from the Technion Israel Institute of Technology, and today I will present my work titled Mining Logical Arithmetic Expressions from Proper Representations. Let's begin with some motivation. Nowadays, we encounter huge databases and data streams. This explosion in data volume has triggered a rapid development of various data mining methods. The general goal of these algorithms is to find interesting relationships between the variables from which our database is made of. In many cases, logical expressions are very convenient for describing the mining results, which are usually called patterns. For example, a stream originating from a vehicle sensor set may include patterns which are identified with abrupt braking. Here, the variable that represents the acceleration of the vehicle participates in a condition. Additionally, this stream could contain another pattern that is identified with dangerous maneuver of the vehicle. This pattern is expressed by two conditions, one for the acceleration variable and another condition for the steering angle. The two conditions form one logical expression, which is a conjunction of the two. Surely, conditions may involve more than one variable with more complex terms. Formally, we define a pattern to be a phrase that is satisfied by a set of observations. I let it be undefined for some observations because in most problems we have many unreasonable situations, such as a vehicle driving at 2000 km/h. Let me also introduce a concept that I use in this work. Soft decision trees are a type of decision trees that allow data points to have dynamic membership distributions on all decision paths. Instead of hard decision functions, each internal node is associated with a multivariate decision functions that routes a data point to its descendants with some probability. The decision of a tree is computed recursively by each internal node as a convex combination of the decisions of its descendants, and the decision of the leaf node is parameterized by a learnable vector that remains fixed during test time. For training a soft decision tree, I used the training procedure described by Frost-Hinton. For every leaf node B, let PB be the path from the root of the tree to that leaf node. Then, the loss for training a soft decision tree is computed as a cross entropy between the true label and the predicted one, weighted by the path probability to each leaf. Moving on to describing my method, let me first give an overview of it. As depicted in the figure, it separates the mining process into two core phases. The first phase intends to learn a representation of the data with the guidance of learning to solve a task. Later, equipped with a learned representation, we move to the second phase to generate patterns on top of it. Specifically, I encourage learning good data representations, which is 1. Informative, which means that it is useful for solving the task, and second, it is simple in the sense that it is easily partitionable. The first qualification is assumed to be achieved by training a model that is denoted by age, which is a composition of two deep neural networks to solve the task. For this, I follow the standard setting of learning the parameters of age by the empirical risk minimization approach and minimize some predefined loss function that is associated with the task. The simplicity qualification is achieved via a regularization term that encourages unscattered neighborhoods, which are expressed by clusters that are compact and well separated. I do so by minimizing a distance-based contrastive loss component as follows. For each observation, I use the learned feature of extractor F to compute its representation. Then, for each observation, I found its neighborhood, which consists of its k nearest neighbors in the learned representation space. Then, I aim to minimize the distance between neighbors and maximize the distance between non-neighbors. I do so by conditioning the neighbors on their proximity, as expressed by the simplicity loss. As can be seen in this term, minimizing it leads to the minimization of distances between samples in the numerator, and also it pushes apart non-neighbors in the denominator. To conclude this representation learning phase, we obtain the parameters of age through training batchwise to minimize both the loss associated with task and the simplicity loss. Okay, after learning a good representation, I move on to the expression generation phase. The learned representation is now used for creating a finite partitioning of the learned representation space. This partitioning is used for self-labeling of the data points. For the experiments that I will present shortly, I use several clustering algorithms, such as Gaussian mixture model and dbScan. After creating the self-labeling, I use it for training a soft decision tree to predict the membership of a data point to a subspace. Finally, note that two leaves of the tree that descend from the same node and represent the same label can be pruned without changing the prediction of the tree at all. Thus, I perform a post-order traversal on the tree and prune leaves of the same label. This results in shallower trees that are simpler in terms of path length and number of parameters, which in turn enhances the comprehensibility of the generated expressions. Now, the soft decision tree allows us to generate expressions that describe its decision paths. However, since the decision boundaries in each internal node are shared across various paths, the conditions extracted using this method are not tight, as shown in the following figure. To address this issue, I tune the decision thresholds of each decision function with respect to the data points associated with each leaf. For this purpose, a data point is a member of a leaf to which leads the most probable decision path. As can be seen in the procedure tune decisions, this is done by iterating over all the members of each leaf and finding the range of thresholds that fit the samples that go through a decision path. To assess the performance and usability of the patterns generated by our method, I performed experiments on real-world datasets. Note that traditional pattern mining algorithms are evaluated in terms of their objective, such as the support of a pattern in the database. However, such metrics are not applicable here because the generated patterns are not intended to be frequent. Instead, I strive to achieve other qualifications. As Occam's razor encourages simple explanations, I use a metric called comprehensibility to evaluate the generated patterns. The first experiment uses a stream originating from a vehicle sensor set. For the purpose of representation learning, I used contrastive predictive coding, which is a self-supervised method for learning data representations. Then, I used Gaussian mixture model for partitioning the learned representation space. An example pattern generated by SIN is the following. Here, the pattern is defined over 10 time steps in a time resolution of 1 sample per second. The first condition contains the steering angle at time step 0 and time step 2. The contrast between the coefficients implies that the steering angle changes at a rapid pace. The second condition focuses on the vertical acceleration. This is interesting because the acceleration changes in these directions may come from downforce that is applied on the vehicle, possibly because of abrupt deceleration. More example patterns are shown in the paper. The second experiment uses a database that contains purchase orders from grocery stores. For the purpose of representation learning, I use the denoising autoencoder, which is an unsupervised method for learning data representations. Then I use dbScan algorithm for partitioning the learned representation space. An example pattern generated by SIN is the following. This case exemplifies the usage of SIN for generating logical clauses, since every binary variable is an indicator for the inclusion or exclusion of an item in a transaction. For example, the condition meat is bigger than 0.5 implies that meat is included in the pattern. Interestingly, the presented pattern can be inferred as a combination of ingredients that make up a meal, which might describe consumption habits of certain people. This raises an important question of whether traditional item set mining algorithms would find such a pattern. In order to answer this question, I've counted the number of transactions satisfying these clauses in the original database. And amongst all transactions, there was only one such transaction, which means that traditional frequent item set mining will not find it, despite being actually an interesting item set. Also, similar behaviors are observed for other patterns that are presented in the paper. I continue with the analysis of the following pattern. This example introduces a new variety of item set mining. While traditional approaches do not support OR conditions between items, this method was able to generate such item sets because multivariate decision functions were used during training the soft decision tree. Hence, it is very expressive and new powerful insights could be obtained from these results. I continue the study by examining the impact of the parameters on the results. The following figure shows the number of resulting patterns for various numbers of neighbors k and tree height initializations, age. Typically, the number of patterns decays and the number of neighbors grows due to the larger neighborhoods, which reduces the number of self-labels. Additionally, a shallower tree initialization results with fewer patterns due to the reduction in the number of leaves. Moving on to the analysis in terms of comprehensibility, I measure the average comprehensibility of patterns generated by each configuration. The average comprehensibility has a very moderate downward trend as the number of neighbors grows. Apparently, it grows linearly as the tree gets deeper and its standard deviation also gets bigger as the tree gets deeper. This suggests that deeper trees are pruned more aggressively. To conclude this work, I presented a method called soft decision tree for logical arithmetic expression mining, SDM in short. Using the soft decision tree, it effectively generates expressive and representative mathematical expressions from the knowledge obtained in the representation learning phase. The experiments that I have conducted on multiple datasets show that SDM has great expressive power and comprehensibility at the same time. For future work, two possible directions can be considered. One is replacing the soft decision tree with different surrogate models for pattern generation, and the second is discovering new representation learning methods from which we can generate representative and very interesting patterns. Thanks.